Hi everyone, my name is Cristian Valladares, and I will be representing our team today. The name of our research is investigating the correlation between performance scores and energy consumption of mobile web apps. And this is a collaboration between Vrije Universiteit Amsterdam and Greenspector. Today I will walk us through the motivation for our research, our study design, what did our experiment execution look like. I will explain the results after the whole empirical analysis, and we will go over a small discussion at the end. So first, the motivation for our research. It starts with a mobile web app. And why did we actually choose the mobile context? It's because the mobile has become such a large segment of internet traffic, and it's actually increasing. And we also concern ourselves with performance analysis tools. Now, what are these tools? They attempt to quantify user perceived performance of mobile web apps. And they emerge because, well, there exists a lot of research that shows that as web applications are perceived to be of poor performance, they lead to user abandonment, and they lose a lot of user engagement, while there exists also a lot of examples in industry of web applications that have been rebuilt from the bottom up in order to improve their user perceived performance, and they started generating a lot of user conversion. So how these performance analysis tools work is that typically they take a mobile web app as an input, and they generate an output of a performance score, which indeed quantifies the user perceived performance, and they also provide generally improvement guidelines. So this serves as a tool that helps developers adopt the best practices in order to improve the performance of their web applications. And this helps in a way such that the process becomes cyclical. So as developers start adopting these improvement guidelines, the performance score increases, and it serves as a driver in the development cycle. We have, for example, Google Lighthouse, web page test, and sitespeed.io as some of the big players. But we concern ourselves with Google Lighthouse primarily, which is open source and actively supported by the community. On the right side, you can see an image of what an assessment done by Google Lighthouse looks like. We focus on the performance aspect. And as you can see, there are many multiple metrics at the bottom that show what is taken into account into this single metric. However, if we focus on the energy consumption analysis, there exists tooling that is able to produce a measured energy consumption from applications. But with regards to improvement guidelines, often these tools do not provide these, unlike the counterparts in the performance analysis. And the consequences of not taking into account energy consumption of applications is that it could also lead to a loss of users. So this research tries to bridge this gap between performance analysis and energy consumption analysis. And we ask ourselves the question, does there exist a relationship between performance scores and energy consumption in such a way that we can better support developers to adopt improvement guidelines? So our research question is, to what extent do performance scores correlate to the energy consumption of mobile web apps? So indeed, bridging the gap between the analysis of energy consumption and performance. So for the study design, we define a 1-factor 3-treatment experiment, and we aim for a balanced experiment, which we will demonstrate in the following slides. The independent variable is defined to be a performance level. So 3 treatments are good, average, and poor, depending on the performance scores. So this independent variable is controlled via the selection process of our web apps, which is selected by means of the scoring that each of these independent web apps achieve. The dependent variable is the energy consumption. So the energy consumption that is upon loading the web app on the mobile web browser, which we will measure in joules. The null hypothesis essentially states that there is no statistically significant difference between the means of each independent performance level, while the alternative hypothesis, of course, states that there exists at least one difference between a pair of performance levels. So the experiment execution, we will start with our subject selection. First, what we do is that we take the Alexa top 100 websites. So these are the top 100 most visited websites in the internet. And for each one of those 100 websites, we get the Lighthouse performance scores. As you can see, statistically, the minimum value is a value of 0.01, while the maximum value is a value of 1.0. The mean and median are both 0.52. After generating these 100 websites, we select according to the three performance levels. As you can see, the scoring cutoffs are from 100 to 75, 74, 245, and 44 to 0. And we perform a stratified random sample. So essentially, we want to have 7 applications per category. In this way, we achieve a balanced study. And the nice thing about this is that we achieve it using real web applications, which you can see from the right side table. And these are applications that are production ready. And as you can see, this is a bit of a view into what the performance scores achieved per website are. So some performance scores, the lowest one here is 0.8, while one of the highest ones is 0.94. Moving on. This slide tries to explain how we perform our energy assessment. So we leverage a professional grade software-based energy profiler, and this is Greenspector, which actually also orchestrates the whole process. But before this takes place, we perform a calibration using defining a probe trust level. In this way, we make sure that what we're collecting is reliable. And we also remove the reference power consumption from the operating system. So we're using an HTC Nexus 9, and we take into account the reference power consumption for this device, and we remove it from our energy collection. We sanitize the operating system and configuration, so we make sure that it's a fresh installation for application. We also make sure that we remove the notifications and automatic updates, and just to make sure that there's nothing interfering with our collection process. Next, we execute the tests using UI Automator. And in this way, we're able to load the mobile web app into the devices. After we're able to collect the energy consumption for, or we're able to execute this application, we wait in order to mitigate the tail energy consumption. What is this phenomenon? Is that the operating system leaves the device in a high-powered state in an optimistic way, such that you are able to make the multiple requests at once without having to power the device with each request. So we would like to actually wait for this tail energy phenomenon to take place. And after we make sure that this we're out of this phase, we clear the device caches and we execute again. So in order to make sure that we have a very clean collection of data. And we perform 25 iterations per web app. The energy consumption values are collected in microwatts. So we try to convert that into energy. So it takes into account also the profiling time. Therefore, we get joules. So next, we move on to data exploration. As you can see from the left table, you get an idea of what is the mean energy consumption per application. Some of the highest one is 193.97 joules. Some of the lowest ones that we can see is 11.83. And you can see from the histograms that it does not show a normal distribution in a way, like so the typical bell curve that you would expect from a normal distribution is not there. We also perform a quantile plot against a normal theoretical quantile. As you can see, it's very curved, while it should be following a straight line. In our research, you can see that we also performed multiple transformations, but none of them yields promising results. But to be 100% sure, we performed the Shapiro-Wilk test with a significance level of 0.05, where the null hypothesis tries to test whether the data that we collected comes from a normal distribution, but we reject the null hypothesis with a p-value of 4.4 times 10 to the negative 7, so a very small value. In this slide, we will see sort of an intuition of where our research is going. So as you can see, low or poor performing web applications are already consuming much more energy than good and average applications. And as you can see from the box plot on the right side, indeed the means are different for each group, having poor performing applications having a very high mean energy consumption, followed by average, and finally good. But for this, we have an empirical study. So we start performing tests to make sure that there really exists a difference between each group. First, we perform the Kruskal-Wallis test with a significance level of 0.5. So we indeed try to test, does there exist a statistically significant difference between the population of its group? So the null hypothesis is indeed that there is no statistically significant difference between each group, but we can reject it with a p-value of 2.2 times 10 to the negative 16. Following that, we try to get an idea of what is the correlation, between each group. So we can see actually from Spearman's rank correlation coefficient that we have a negative correlation. So as the performance score increases, the energy consumption should increase. Next, we try to see what is the difference between each group. So as you can see from the density curve, we have each independent group, and we perform Dunn's test, and we perform a Bonferroni correction just to make sure that we are performing this test without making any error. So between the good and poor groups, we have a p-value of 3.7 times 10 to the negative 56. So we're saying there exists a statistically significant difference between the good and poor groups, which is the pink and the blue groups that you can see in the density curve in the right side. From the average and poor groups, we can also see that we reject the null hypothesis. And we can see that, yes, from the density curve, the difference between both, and as well for the good and average with a 0.023 p-value. And we want to measure the effect size. So we can see that for both good and poor and average and poor, we have a very large effect size. So we can see a very large difference between those two group comparisons. But with good and average, we can see just a very small effect size, so it's a very small difference. So as you can see from the density curve, the overlap between the pink graph and the green graph, there's quite a bit of overlap, but there still exists a statistically significant difference. So as a discussion, we can see that this experiment shows a negative correlation between performance scores and energy consumption. And we know that performance analysis tools like Google Lighthouse are able to provide some preliminary insights into what is the energy consumption of your application. So if you have a poor performing application, you can confidently assume that your application might have a higher energy consumption. And as you progress, you can assume that you're making gains in minimizing the energy consumption of your applications. However, we always advocate for still using dedicated energy measurement tools, as they are still necessary to get a granular analysis of your particular web application. So concluding remarks, we started with a research question: to what extent do performance scores correlate to the energy consumption of mobile web apps? We created one-factor three-treatment experiments taking into account the independent variable of performance level and the dependent variable of energy consumption. We performed a data analysis, which concluded with a hypothesis testing, which asked, does there exist a significant difference between each different performance level with regards to energy consumption? And indeed, we found that there is. And we identified a negative correlation between the energy consumption and performance scores. So with this, we conclude this talk. Thank you very much.